Good.
Okay.
Okay, thank you very much. Just set the... Okay, so let me first thank the organizers for the invitation to speak at this very nice conference. I find the idea great for a conference that would allow students to choose a specialty or to see what people are doing currently in mathematical research. So actually, I was a participant of this conference that Professor Hayat mentioned in 2020, and I really like the way that the event has gone. So in the way that it's not only for just showing the stuff we are doing to students of the first years, but also trying to open up directions of research for people who would like to do research in mathematics. Okay, so I'm going to speak about a topic called dimension-free estimates for Hardy-Littlewood maximal functions. And a large part of this is my joint work with Jean Bourgain, Mariusz Mirek, and Eli Stein. And some of the things that I'm going to speak about are recent works with people from Wrocław, Dariusz Kosz, Paweł Plewa, and Tomasz Szarek. Okay, so before I'm going into to describe what is the area, let me just say that I would like to convey that there are some connections in between this area and other parts of mathematics, more than trying to give you the proofs of the results. So it will be more about telling you what are the connections and what are the ideas used in the proof, rather than presenting a complete description of the subject. So, and I would like to be rather basic, but there will be some parts which I would ask you to take for granted. Actually, large parts of that, but some of them will have some sketches of the proofs that I think everybody can understand. Actually, parts of the proofs are, I think, comprehensible to high school students, because they are just about sums of sines or cosines and trying to get a bound for those signs. We'll see later on. Okay, so the first, before I'm going into the subject, let me just say that, start very basically. Let me just recall or tell to those of you who haven't heard about it, what are the LP spaces. So if you know what is the Lebesgue measure, then we can think of the space of functions from Rd to Rd. So these functions need to be measurable, but for us, actually, all of the functions that we are going to apply the objects of our interest will be continuous, and we can think that there are C infinity. So the word measurable doesn't matter to us at all. But formally, these functions are measurable, and we would ask that the integral over Rd, which you can think that this is just the iterated integral over R's of the function f, is finite. So this is what is called the LP space. It's one of the first objects that appears in measure theory when we define the Lebesgue measure. Okay, and then we define a quantity called the norm on the LP space, which is just the integral over Rd of f raised to the power p dx raised to the power 1 over p. The reason for that is that if you make the definition of the norm in this way, then it's really a norm. So this quantity really is a norm in the sense of linear algebra or functional analysis. Okay, and here we take p between 1 and infinity. And the reason for this is, again, that this is a norm in this regime. And usually for us, what will matter will be p from strictly between 1 and infinity. So the interesting part is for p between 1 and infinity. There are some questions for the endpoint p equal to 1, but I'm not going to touch on them. Also open questions and hard, but I'm not going to speak about them very much in this talk. Okay, so as I said, dx denotes the Lebesgue measure on Rd, and we write a, the modulus of A, to denote the Lebesgue measure of the set A. It may be a bit confusing, but, well, in a way it makes sense, because the modulus of A means for us the size of A, and the size is in the terms of the measure. So this is the size in terms of the measure. Okay, and then so this part might be, I'm going very slowly because some of you might not have had function analysis yet. So for those who had, this is easy, and I'm just taking a lot of time to explain the basic stuff. But for those who hadn't, I think it's important to be slow here, so that you can take time to understand what's going on. So Now, an operator T, denote operators bar T, is a mapping, which means a function that takes one function in LP to another function in LP. So for example, let me just write an easy operator. Let's say that Tf of x equals f of x plus 1. So that's an operator because it takes one function and makes another function out of it. And actually, it's a bounded operator on all LP spaces. It's called the translation. Okay, so an operator is going one level higher than functions. So it's not a function that assigns a number to a number, say, or a number to a vector in Rd, but it is a function which assigns one function to another function. And these kinds of objects appear very, very often in analysis. And many parts of analysis are actually stated in the language of linear operators. So properties of linear operators are of crucial importance in many parts of analysis. Okay, and we say that the operator is linear if it maps linear combinations of functions to linear combinations of functions. So as one could guess. But also another class of operators will be even more important to us. So we say that an operator is sublinear if it preserves multiplication by scalars. So T of alpha f is alpha T of f, and it is subadditive, meaning that if you apply it to a sum of functions, then it is controlled by one of the operators on the function plus the other operator on the function. Okay. So these are the this is the description of the most general description of the objects we are going to deal with, but we'll be more specific in a moment because we will not consider, of course, all the operators on LP, but some specific classes of them. Okay, so let me go to, if you have any questions, then just please interrupt me during the talk. Okay. So the general setting we'll be working with is a setting of specific classes of operators where one parameter plays a very important role, and this parameter is called the dimension. It appeared already above, but perhaps I have not underlined the importance that this parameter is important to us, because often for some of the estimates in analysis, you just treat the dimension as a parameter that is there, but it doesn't really matter because all the results translate to any dimensions in a way. But for us, it will be important that the dimension is a specified parameter, because later on we would like to control the objects we are interested in terms of this D. Okay, so D, throughout the talk, D will denote the dimension, and the spaces where we'll consider these D-dimensional spaces will be either sometimes RD for the first part of the talk, but later also ZD. So Z is just the integer lattice, the integer points, and ZD means, of course, Z Cartesian product with Z, and the same with RD, of course. So we consider a family of sublinear operators TD, and we think that each of them, each TD acts on one of the spaces LP over. So for each dimension, we have an operator which we call TD. In a moment, we will see that this is natural, and many operators there are many families of such operators that are interesting. Okay, and we will say that the family TD has dimension-free estimates on the particular space LP if this inequality holds. So for a moment, let us forget about this supremum here outside, but let's just think about this inequality here. Okay, so it says that if you apply the operator TD to the function f, then you have to control this quantity, the norm, this LP norm of this quantity, by a constant C of p times the LP norm of f. So I could have written it in another language by just saying that this basically means that the operator is bounded on LP. So this remark is for those who had functional analysis. So, but if you don't know this term, then it essentially means that one can control TD of f in terms of f. So for example, if f goes to 0 in the LP norm, then TDF also has to go to 0 in the LP norm, which is, by the way, equivalent with this estimate. Okay, but the crucial point for us is that we will be very much interested in the size of this constant. So this line of research is sort of in between trying to get the optimal constant and trying to get any constant. Quite often the proofs that one has of bounds for operators just give you some constant which is large, and there is one line of research which tries to get the optimal constant, which is harder than what we are trying to achieve, because we are trying to get a good constant but not the optimal one. We'll see in a moment what I mean by that. So we'll ask that the constant C of P here depends only on P but not on the dimension, not on D. So it will be very important to us to get constants which do not depend on D. So we are interested in good constants, but not the best constants. Okay, so let me give you some examples of a situation where we have such families of operators. Actually, many of them are natural, and for many of the cases, getting the constant is easy, even the optimal constant, but not always. Okay, so first let me give some examples of linear operators for which you can ask about the size of the constant. So we take the first example I would like to give, since I'm mostly working in harmonic analysis, the Fourier transform. And the Fourier transform of a function is another function denoted by f d of f evaluated at psi is just the integral over this function f with respect to this exponential factor. So this exponential has a lot of oscillations because if you recall, e to some strictly imaginary power is just the sine of 2 pi x psi. Sorry, it's wrong. This is just sine of 2 pi x psi with an I plus the cosine. So x dot psi means the inner product, the scalar product. Okay, so it has a lot of oscillations and it makes one function out of the other function, but it has some very useful properties that are applied in many areas of analysis. And one of them is called, maybe one of the most important of them, is called the Planchard formula, which for this specific definition of the Fourier transform says that the L2 norm of the Fourier transform is the same as the L2 norm of the initial function. So I recall that this L2 norm was just the integral f squared to the power 1 over 2. Okay, so it says that the L2 mass of the function is preserved by its Fourier transform. So for example, it has translations to not only to mathematics, but also to physics. It means that the energy can be computed. Essentially, the L2 norm of the function is related to energy in physics, and it means that it can be computed by just taking amplitudes at various frequencies, because this psi here may be regarded as a frequency. Okay, so it's called, as I said, the Planchard's theorem, and it means that for the Fourier transform, you see that I defined Fourier transform for each of the dimensions d. So I have a family of operators defined on each dimension d, as I wanted to. And it says that this constant C of P for the Fourier transform, in the case P equal to, is equal to 1. Not only that, but actually this is the optimal constant because it's an isometric, it preserves the norm, so you cannot get a better constant. It's rare that you have this situation, but here it's quite obvious if you know Planchard's theorem. Okay, so for the Fourier transform, it has dimension free. We may rephrase the obvious fact that the Planchard's theorem holds in a way that the Fourier transform has dimension free estimate on L2. Okay. Later on, we'll go to harder operators, but let me start with this. Okay, and then the next thing I would like to mention is the Gaussian kernel. So you take a function on each dimension d, you take the function defined in this way. So it's a Gaussian e to the minus modulus of x squared over 4 times the factor. And this factor is such that the integral of this kernel is 1. The reason for that is this. Okay. And then we define the operator Td of f by a convolution of f with this function hd. And the convolution is, if you haven't seen it, it's just this quantity. Okay. And then it turns out, by a result which is called Young's inequality, that you have a constant, you have an estimate on all LP spaces, C of P from 1 to infinity, including both the endpoints 1 and infinity, with a constant in front, which is not here, but if the constant is not there, it's 1. Okay, so it means that the convolution with the Gaussian kernel, this kind of operator, has dimension free estimates on all LP spaces with constant 1. So the Fourier transform had it just on L2. This one has it on all LP spaces with constant 1. So yeah, very good for, I mean, very precise dimension-free estimate. Okay. So these were two examples of linear operators, but now let us go to more complicated examples of sublinear operators. Actually, the first of them is not so complicated, but the last already goes into the direction of what I would like to speak about. Okay, so the first is just about L infinity estimates. So you take a function which integrates to 1, and once again, and consider dilations of this function. Dilations, I mean that you scale here by x over t, and this t to the minus d in front is just to make sure that the integral stays 1. So it's just the corrective thing to make sure that the integral stays 1. And then it turns out that if you compute the supremum of gt convolved with f over this, then you have an estimate with a constant 1 in front. So this L infinity, if you haven't seen it, you can just think that this is the supremum norm. I mean, here it's written essential supremum in the definition, but for us, functions are continuous, so I can just safely erase the word essential. So it just means supremum. So the L infinity norm is the supremum value of the function. Okay, and it turns out that you have this kind of estimate. This one is easy to prove. I mean, if you just use the Young's inequality that I mentioned before, but the last example I would like to show before going to what we are doing is about the Gaussian maximal function, and this is already harder. So this is where difficulties start. So we consider once again the Gaussian function. Once again, so recall that if t was equal to 1, that this is the function that I have taken before. So t equal to 1 gives 4 pi to the minus d over 2, e to the minus x squared over 2 over 4. Okay, over 4. Yeah, and then we make a convolution with this function ht and take the supremum over t outside. Okay. And it turns out that this has dimension, in other words, this has dimension-free estimates on all LP spaces, because all apart from 1 infinity, but with a constant that does not depend on d, because of course here the family depends on d, but the constant does not grow with d in front. But this is not so easy because it already goes into an area-chord semigroup theory and also martingales. So I mean the proof can be performed by using martingales. So it's not that you can I just give you several inequalities and I say prove it with that. It's not so easy. You have to study a little bit to understand this inequality. So it's already, this one is already much harder than all the three above. It takes probably a lecture to describe it, whereas those three above, probably I can describe it in 10 minutes, each of them. Okay, so yeah, having shown you some examples of the dimension-free estimates that hold or do not hold, let me go into the actual objects that we were interested in. So the actual objects that were interesting for us are called Hardy-Littlewood maximal functions. And I would like first to describe something that has been done in the continuous setting, just by saying what are the results. And then I would like to go in the second part of the talk to the discrete setting and to show you what kind of estimates would be desirable to obtain our results and why they are not so easy to prove. But first, let me start with the continuous setting. Okay, so the first Hardy-Littlewood maximal function that was out there in dimensions higher than 1 was the one defined for the Euclidean balls. Okay, so we take this already appeared, but I haven't written explicitly. So x denotes the length of the vector x, the Euclidean norm. B denotes the closed Euclidean ball in Rd. So the set of those x's in Rd that have the Euclidean length less than 1. Tb denotes the dilation of the ball, which means that just we take points from the ball and scale it by t. And now the important part, mtb is the average. Here, it is the average over tb. I will use the word average because see that here I take tb, but I normalize it so that I have the measure. Recall that this was the Lebesgue measure of the set. So I normalize it in front so that this is really an averaging operator. By that I mean, for example, that if you would like to take f equal to 1, then this operator would be 1. Mt b1 equals 1. So this is really an averaging operator. It takes a function and makes an average out of it, some average. Okay, not really just of the function, but of its translation. So the point x appears here, and it means that we shift the function f and then take the average around this point x of the function. Okay, and then the important object for us would be not really this average, but the maximal function of it, which means we take the supremum over all times t greater than 0 of these averages. And we would like to ask if this object, this m star b, has dimension-free estimates. This MTB itself, it has dimension-free estimates for easy reasons, which I don't want to indulge right now, but this one is harder to show that it has dimension-free estimates, and it was obtained as a first result in this line of research by Eli Stein in '82. So it turns out that if you take the Hardy-Littlewood maximal function over the Euclidean balls, then it has dimension-free estimates on all, I haven't written what is p, but p is between 1 and infinity. So it has dimension-free estimates, it has dimension-free estimates on all LPs from 1 to infinity with a constant that just depends on p. So the family of maximal functions over of the Hardy-Littlewood maximal functions over Euclidean balls has dimension-free estimates on all LPs. But this is very specific to the set B. And by the way, before that, before Stein's result, it was only an estimate of this sort was known. So we have constant which depends only on p, and then 3 to the d. So 3 to the d is a nice theoretical number, 3 to the d, but when d is equal to 1000, it's already larger than the number of atoms in the universe. So it's not it can be quite large even if the dimension is not very large. So it's exploding exponentials explode very fast if the dimension is large enough. So it's not, for some purposes, we would like to have a smaller constant, not 3 to the d. Okay, so this is what happened for the maximal functions over the balls, but then let's think if we can replace the ball B2 here by some other set. Sorry. Yeah, so what happens if ball is the Euclidean ball, but what happens if you would like to replace it by the cube? So the cube in RD is just a copy, product of the segments -1, 1, d times. So in an obvious way. And then this just means that x is in the cube, if and only if all of the coordinates are smaller than 1 in the modulus. Okay, so if x is in Q, and we consider this quantity the Euclidean norm of x, then each of the summands here, xj, is smaller than 1, because I said that x is in Q. So it means that xj, x1, x2, etc. is smaller than 1. So we have a number of ones here, 1 plus 1 plus 1, d times, and then this gets raised to the power 1/2. So what happens is the square root of d. Okay, so if x is in the cube, then x is also in the Euclidean ball of radius square over d. So you see that there is a comparison from going to one set to the other, but you use a square root over d in the process. On the other hand, if x is in the ball, then we are asking that sum of the coordinates squared is smaller than 1, so each of the coordinates has to be smaller than 1. If one was larger than 1, then the sum cannot be smaller than 1. So it means that the maximum of all the coordinates is smaller than 1. And this, by definition, means that x is in the cube. So the moral of this short argument above is that if you take, well, I add the factor t here, but the argument would be pretty much the same. It says that the dilation of the ball is inside the dilation of the cube, and the dilation of the cube is inside dilation of the ball by an additional factor square root of d. Okay, so the sets are comparable, but you lose in one way the comparability constant is 1, but on the other way it is square root of d. And what are the consequences of this? So one would perhaps would like to try to deduce an estimate for this maximal function. So see that difference is that I don't have a ball here, but I have a cube. So I'm taking averages once again, but over cubes, not over balls. So I would like to compare this maximal function with the previous one of Stein. And the problem is that because in these inclusions you have this nasty square root of d here, you will get an estimate from the result of Stein, but it will get an additional factor of d to the power d over 2. And the reason for that is that scaling of a set and measuring Lebesgue measure gives a factor t to the d. So you can think that square root of d to the d is d to the d over 2. Okay, so you can transfer one result from the other, but you get a even worse factor in front, not only 3 to the d, but d to the power d over 2, which is much larger than 3 to the d for large d, so even worse. So there is no way of transferring dimension 3 estimates in this manner. Okay, so let me go further, and then more generally, we would like to consider not only balls and cubes, but more general sets G. And the sets that are interesting for us are called symmetric convex bodies. And well, this term just means in the theory I'm mentioning that this is a compact set with non-empty interior with the property that x and minus x are at the same time in G. Okay, so it's a compact set with non-empty interior, which is symmetric. Okay, and then we make once again averages over such a set. So you see that now I have replaced the ball B with G here and with G here. So it's another kind of average. It's again an average because if you take empty of 1, then it is 1. Because I would have just 1 here, and then it will be the integral over Tg of 1 divided by the measure of Tg, which is 1. Okay, so it's really an averaging operator, and I'm not interested very much in this operator, but in the supremum for all times of this operator. Okay. So it's defined over here. Sorry. So this is defined here, and this is it's the maximal function corresponding to those Hardy-Littlewood averages. So Hardy-Littlewood maximal operator over G. Okay. And it turns out, that similarly to the cube, every symmetric convex body G is contained in some ball and contains some ball and is containing some ball. This is easy because I said the set was compact with non-empty interior. Non-empty interior means that there is a ball inside, and compact means that there is a ball outside. So it's straightforward. But the problem is, as we already observed in the cubes, that those constants A and B probably depend on the dimension with high chances. So if you would like to transfer some estimate for m star of G from Stein's result, you will get a constant here of C over B depending on A and B to the power D. And for example, for the cube, it was the square root of D, which resulted in D to the D over 2. So pretty bad. And for other sets, probably it will be even worse. Okay, so as I said, the simple comparison does not give dimension 3 estimates. And another problem is that the argument of Stein only work very specifically for the Euclidean balls, because there is a group acting on them called the rotation group. So if you rotate the Euclidean ball, you get the Euclidean ball again, basically, but it's not anymore true for other convex sets. For example, if you rotate the square, just a very tiny angle, it's not the same square anymore. And if you rotate the disk, it is still the same disk. So this is why Stein's argument worked there, but it cannot work here. And here entered Jean Bourgain. So at the time, he was doing some research in Banach spaces where these kinds of convex sets were important, because maybe let me skip one step further. Sorry. No, sorry. Okay, it's here. So those convex sets are important because I don't want you to go into the details here, but basically why such convex sets are important, one may ask, because every norm on RD is related with a convex set of this form. So essentially they give, by this thing called Minkowski functional, they give all the norms on the RD space. So on RD space, there is a bunch of ways we will measure the length, a bunch of norms, and all of them are equivalent. This is an easy theorem. But the point is that but not with the same constant in front. So the point is, how do they appear, those kind of norms? And they appear because there are these functionals of the convex set. So this is more directed, sorry, this comment is rather for people who have functional analysis. So those who haven't had it just can ignore it. It's not so important at this point. Okay, so let me come back to what we were above. Okay, so what Bourgain proved was that in 85, that there is a universal constant. I haven't written it, but this universal means surely less than 1000. So for example, 1000 is okay. Such that for not only for all dimensions, but also for all symmetric convex bodies, G, the maximal function over G, m star G, F, has dimension 3 estimates on L2. So P equal to here. Okay, so it's in a way it's weaker than Stein's result because it doesn't cover P less than 2. But on the other way, it's much stronger because it covers all symmetric convex sets. So it doesn't depend that it was a specific ball or something. Okay, so I'm not going to say how this point below is true, but the crucial point for us is that the proof relies very, very much on properties, on computations and estimates for the Fourier transform of this set 1 over G. In a moment, I will tell what G tilde is. So I want to convey the message that the Fourier transforms estimates are at the heart of the proof, even though we had the maximal function in front. So at first sight, there is no Fourier transform there. It's just an average and then taking a supremum, so no Fourier transform. But actually, what is important for this proof are Fourier transform estimates. And even more, I would like to mention what kind of these estimates are, because they are also used later in the discrete context, which is related to number theory more than this. Okay, so the point is, the first point in the argument of Bourgain was that he realized immediately that one can replace the convex set G by another convex set G tilde if you apply a linear transformation A. And linear transformation means a matrix here. So if you take a set G and you map all of its points by a matrix A of X, then you get another symmetric convex set G tilde. And it turns out that the maximal functions are the same. I mean, it's not that the maximal functions are the same, but the norms of the maximal functions are the same. So it doesn't matter if we take G or any mapping of the set G. This is true in the continuous setting, but it won't be true anymore in the discrete setting. So this is one point that makes the discrete setting later harder. So for example, if you consider the Euclidean ball and consider this ellipse, I just made it up yesterday. So it's just an ellipse with some factor in front, like 1 + 1 over I squared or whatever, doesn't matter. Then one is mapped to the other by a linear transformation, which can be easily understood what it is, because it just means mapping these coordinates xj by appropriate factors. So ellipse is equivalent to the ball by a linear transformation. So dimension-free estimates for the ball imply dimension-free estimates for the family of ellipsoids in all dimensions. So for example, ellipsoid is easy from this perspective. Okay. So this was proved in 1995, and then then what is the disposition that we are taking the body to? Because I said that we would like to replace A with some set G with some other set G tilde. Okay, and what is the transformation? So not really what is the transformation A, but what is this G tilde I would like to speak about? And it turns out that the good idea to put is to get this G tilde in something called the isotropic position. So isotropic position means that all of these quantities, so you integrate G over this xi psi I squared, and then this happens to be L of G times psi squared. So this is the definition of the isotropic position. So a body is in the isotropic position if its Lebesgue measure is 1. By the way, this already excludes the ball because its Lebesgue measure is small, not 1 in large dimensions. And this quantity here is a multiple of psi squared. So for example, what this implies is that if you take, say, psi equal 1 and bunch of zeros, then on the right we will have 1 because the length of psi squared is 1, because it's just 1. And on the left, the only thing in this inner product that is not 0 will be x1. So for example, it means already that in this case, L of G equals, and this quantity L is called the isotropic constant of the convex set. Okay, so a major conjecture, not in harmonic analysis really, but in asymptotic convex geometry, is whether this constant. So I gave you a definition. I have given you the definition here, but the one who could ask if this constant is really of a constant order, because it's a constant in each dimension D. Or sorry, it's a constant for each convex set G, but perhaps it depends on the dimension. I mean, perhaps it can grow larger if the dimension grows larger. And the conjecture as subject of functional analysis called asymptotic convex geometry is whether this constant is, say, between 10 and 110. So it's in a way interesting because it has been open for 40 years and it's related to other conjectures, but to state it, we really don't need to know anything apart from integration of functions in RD. So many of the conjectures in mathematics, you need to know something to understand why they are difficult or what's the problem with proving them. But for this, I mean, it's a conjecture which can be stated to a first-year student if he knows what is the integral over a function. Okay, so this is unproved. Last year there was some progress on it, a significant progress, but it's still unproved. Okay, but since I see that I'm already a bit running late, let me just go to what are the important Fourier transform estimates for what we are doing. So okay, so we have this this convex set G, which we would like to put in the isotropic position, because then I said that this is the important position to make the set with. And now we will consider objects which are just the Fourier transforms of the characteristic function of G. So I recall that the Fourier transform was defined here. And if you apply it to the characteristic function of G, it just becomes the integral over G of the exponentials. Okay. And precisely what kind of G's we would like to take? We would like to take the G's that are in the isotropic position. Okay. So this is, I'm not, as I said, I'm not going to say why this gives the dimension-free estimates for the maximal function, but I'm just going to show you what kind of estimates are needed to get it, what kind of Fourier transform estimates we are happy with to obtain, to prove the results. Okay, so the kind of the Fourier transform estimates that we are very happy to have are these three. So, for example, this three below prove already Bourgain proof. I mean, apart from 10 pages of some machinery that is known how to produce, they prove the Bourgain's theorem. So they are really at the crux of the matter there. Okay, so we take a symmetric convex body in the isotropic position, which means that recall that the Lebesgue measure is 1, and the condition that yeah, the other condition with those equals L psi squared. Okay, and then it turns out that for all psi's in RD, you have three estimates. So first of them is at 0. At 0, I mean that it is important when psi is small. So when psi is small, mg of psi minus 1 is controlled by a constant, which turns out to be at most 150, times the isotropic constant of the body, times the modulus the length of psi. And now remember that we do not know if this constant L is independent of the dimension. So it is a constant, depends on the set G, but we have no idea if it is independent of the dimension. So there are estimates for it, but not independent of the dimension. But very good estimates, very precise from the last year, but still not independent of the dimension. Okay, so this is the estimate at 0. At infinity, we would like to have that if psi gets large, then this has some decay. So it means that there is a psi in the denominator here. And if psi gets larger, then this gets smaller. And once again, there is the constant L of G, which we do not know what is the size of, but the important point is that it is glued, always glued together with psi. So it's not that we have L of G and then something 1 over psi and then L of G times psi, but they are always glued together. So this is what makes the arguments later work, despite the fact that we do not know what is the size of L. Okay, and the last estimate is kind of a differential estimate, which we don't need to really read it right now, but there is an estimate for a derivative of the sort. Okay, so yeah, let me finish this first part of the talk. We've just, okay, so this three estimates give you the result of Bourgain, apart from some standard techniques that are known, not easy to describe shortly, but there are known. But then let me just, before going further to the second part of the talk, let me tell you what is the main conjecture in this field. So in 1 year later, after Bourgain and Carberry independently proved that you can broaden Bourgain's result for P, from P equal to 2 to P greater than 3 over 2. And since then, since 86, nobody knows if you can do it for P between 1 and 3 over 2. So the conjecture that is stated is whether, it's called the Bourgain maximal function conjecture, if you can prove some dimension-free estimates for all symmetric convex bodies in all dimensions, but in the full range from 1 to infinity. So for 40 years, nobody knows how to get below 3 over 2 in this kind of estimate. So it's an open question for 86. And about 3 years ago, we made some progress on this conjecture. Essentially, we reduced the conjecture to an estimate for the difference of this sort. Okay, so this means that you have some Lipschitz estimate for the difference of the two operators. Difference seems to be easier than the maximal function, so it allowed us to prove some other results, but still the conjecture, the main conjecture is open. Okay, I think it is a good time to make a break. Okay. So yeah, we see each other.
Okay, at 10. I think let's reconvene at 10, precisely at 10.
Okay.
Okay, we may resume, please.
Thank you. Okay, so in the first part, I was speaking about Hardy-Littlewood maximal functions in the continuous setting. So we had RD, then the Lebesgue measure, and then some averages, and some maximal functions, and we wanted to know if the estimates of these functions are independent of the dimension. But now, in the second part, I would like to speak about a similar question in the discrete setup. So let me comfort those of you who are really not very familiar with Lebesgue measure that this time we will only consider sums. So essentially, the questions that I'm asking could be understood by people who are in the high school, in theory at least, because there are no integrals, they're just sums. Okay, so let me go into the objects that I'm going to speak about, to describe them. All right, so in the discrete setting, we are once again considering symmetric convex bodies, and I recall that this meant that the set was compact, had non-empty interior, and it was symmetric about the origin. But instead of just thinking about the direction of TG, we would like to think about TG intersected with the integer lattice ZD. So ZD is just Z times Z times Z. Okay, so we are now asking about the set of those integer points, of those tuples of integer points that lie inside the convex set TG. Okay, so we are making, as before, we make an average, but this time as I said, I'm going to, we are in the discrete setting, so we don't have integrals but sums. So by the way, I will keep using this notation to denote the number of lattice points inside the set TG. So it will cause no confusion simply for this reason that I'm always writing the intersection with ZD here. So if you see intersection with ZD, it means it's not the Lebesgue measure, but counting lattice points in this set. Okay, so I consider this kind of averages. So now bear in mind that M is not the Roman M, but it is the calligraphic M, to distinguish from the previous set. So I'm thinking about averages. Now it's again an averaging operator, because if you take the function equal to 1, so M, T, G, 1, you won't have, in the sum here, we'll just have ones, and then the sets are the same. So this is the number of, this will be the number of lattice points in the set, and it is divided here by the number of lattice points. So it is 1. So it is really an average. And then we are thinking about the maximal function corresponding to this object. Okay, and we would like to ask the very same question, a similar question, if you can prove any dimension-free estimates. Estimates which are not dimension-free are, well, maybe not easy, but standard in a way that people know them for many, many years. But we would like to ask about dimension-free estimates. So another change from the continuous setting is that we are not, as I said, we won't be in the continuous setup, so there is no RD, there is only ZD, and the replacement for the norm LP of RD is the norm LP of ZD, and the difference is that we don't have an integral here, but a sum. So you sum all the lattice points in ZD inside all the lattice points in ZD, the function f of x to the d. Actually, I'm saying it's a function, but you can think that it is a sequence, because well, each of the coordinates is from Z, so on each coordinate is an infinite sequence from minus infinity to infinity, and just d times, applied d times. So I use the term function, but you can think that there are sequences, basically. Okay, and the space small LP of ZD is the space of all functions or sequences from ZD to R for which this quantity is finite. Okay, so this is the definition of the norms. But let me, before going further, let me say what are the problems compared with the continuous setting. So the first problem that appears is that there is no scaling. What do I mean by that? I mean that, for example, let me draw here a little lattice on Z2, on R2. So these are the lattice points. Okay. And now let's say we have a set like this. And now if you dilate this set, you are not anymore in the lattice. So if I make an appropriate dilation, then I am. But if I make a dilation like by 1/2, then these points are not anymore in the lattice. So I cannot dilate the set because I'm going out of my lattice and I want everything to stay inside the lattice. In RD, this was not a problem because if you divide the set, you are still in RD. And here, if you scale the set, you lose this property that you are in ZD. So you cannot scale the set. And why this may be a problem? Well, because you remember that for the Fourier transform estimates to work, I said that you need to put the body in the isotropic position, which, by the way, means also scaling. So I cannot do it right now here because I have no scaling. So you already at this stage there is a problem. Another maybe even of another reason, there is another problem that now you don't really need the Lebesgue measure of the set. For example, it is well known what is the Lebesgue measure of the Euclidean ball. It is something of the sort d to the minus d over 2 times something that's of the sort e to the minus d. Maybe I'm not extremely precise, but it is well known. There is a formula expressing gamma functions. This size is perfectly known. It's not so much easy to say what is the size of the number of lattice points inside the set. I mean, it is known if the radius here is large. So this is well known if t goes to infinity. But we don't have scaling, so we cannot think that t is, for example, 1. And we would need to also say what is the size for small t's. You will see in a moment that this is a problem. Okay, and as I said, these problems are real. So it's not that you can just walk around them easily and say that you transfer one result from the other. In a moment, you will see why. Okay, so yeah, the first result that says that the problems are real is concerned with a negative, with a counterexample. So one might pose a conjecture that you have a dimension-free estimate, say on L2 for all symmetric convex sets. It was the case I recall that this was the case in RD. This Bourgain's L2 result said that for all symmetric convex sets, you have a dimension-free estimate continuous on L2. Okay, but now in the discrete setup, there is a counterexample by Bourgain, Mirek, Stein, and myself from 3 years ago, that for each dimension, let me read it out loud and then explain what it means. For each dimension, there exists a symmetric convex set, actually an ellipsoid, such that for some function, this constant is C of P, but times log of D to the 1 over P. So what's wrong with log of D? Well, the wrong thing about it is that it goes to infinity. So there is no uniform control. There cannot be any uniform control for all symmetric convex sets. So there is a counterexample that says that this question in the discrete setup may be much more connected with specific convex sets rather than all of them, because for all of them, it's simply false. It's not only false for p equal to 2, but it's false for all p's greater than 1 and smaller than infinity. So the growth is not extremely fast, it's the log of d, but still there is a growth. So you cannot hope to have an estimate like in the continuous setting in the discrete setup as well. So this is in sharp contrast with the continuous setting where, as I mentioned before, the ellipsoid is essentially a ball in the continuous setting because it's just a ball mapped by some matrix, which can easily be deduced what is the matrix. So for the ball case, it is true. For the continuous case, it is true because the ellipsoid is not distinguished from the ball. So it just follows from Stein's result. Okay, the important point is that this problem, this growth of the dimension norm, appears really for small values of t. So it's also in connection with what I said, that if t is large, then essentially the number of lattice points should be something of the Lebesgue measure of the set. But if t is small, it's not anymore true. And this is why this problem appears for t small. Okay. So let me raise another point why the discrete setting is harder. So the previous example showed that the obvious counterpart of Bourgain's conjecture in the discrete setup is false. But now it turns out that the discrete constant is always larger. So it means estimating it is always more difficult. And this is a result from the last year by Darek Kosz, Mariusz Mirek, Paweł Plewa, and myself. So we proved that if you denote by C of PG, the optimal constant here, so this is the optimal constant in the continuous set. So the best constant that you can have for all functions in the continuous set. And if you denote by calligraphic C of PG, the optimal constant in the discrete counterpart of the question, then one is always smaller than the other. So the discrete setting is always harder than the continuous setting. Okay, so discrete question is harder, but well, I only gave you some negative examples. I'm saying that I'm just complaining that we cannot do anything so far, but there are some things that we can do. Some of them are easier, some of them are hard. Some of them are connected with number theory, and some of them are connected with combinatorics. You will see in a moment. Okay, so what can we prove? So first positive result of this sort is that if you define this constant C of G, so it's a constant which I would like to contemplate for a moment. So for a symmetric convex set G body, we say that C of G, little c of G, is the smallest radius such that the dilation of G by T contains the cube. What is Q is written here. So the Q without the subscript was just the unit cube minus 1, 1 to D, and this is the cube which has diameter 1. So it's the one that has the Lebesgue measure 1. For example, Q1/2 is 1. Okay. So this is the smallest constant by which you can scale that the cube can be put inside the dilation of G. For example, for the ball, for example, this constant is right here, C of B equals square root of D after a second thought. It's related with what we computed before, that if you scale the ball by square root of D, it will contain the cube, but you have to really scale it by square root of D to make it true. Okay, so also 2 or 3 years ago, we proved with Burgen, Miller, and Stein that if you restrict the supremum in the definition of the continuous maximal function to large t's, in the discrete function to large t's, by large I mean larger than C of G times D. So for example, for the ball, C of G, I said that it's square root of D. So it means a restriction to T greater than D over 3 over 2. So this regime. Okay. Then apart from a factor 10 to the 4, you have a control in terms of the continuous constant. So apart from the factor 10 to the 4th, you have a control in terms of C of PG, which is the continuous constant. So the problems are an equivalent, but for large times. So in a way, it's related with the fact that, well, if the sets that you are thinking of, for example, TG, are very large, then for them, whether it's the lattice set or RD is pretty much the same. But if they are small, then it really matters that we are working with the lattice, not with the continuous counterpart of the, not with RD, but instead with the lattice. Okay, so this is a positive result. For example, what does it give for specific sets? So it says that the dimension question is really harder. I mean, that you really have to do something for small t's, smaller than C of G times B. And what is this C of G for various sets? I mentioned that for the ball here, C of B, well, it's actually over 2. So for the ball, it's square root of D over 2. One can compute it. And then it means that the question is hard here for T greater than 1/2 to the power D over 2, the D to the power 3 over 2. Okay, and what is it for the cube? Well, for the cube, it's basically, I recall that in the definition of C, there was not this cube, but this one. So for this reason, one can easily compute that, for this reason, one can easily compute that C of Q is 1/2. So it means that for the cube, the question is hard only here. So in a way, for the cube, it's easier to transfer. For the ball, it's harder to transfer. Depends on the set, how hard it is to transfer the estimates. But still, even in the cube case, we don't know how to, in this way, we cannot treat T smaller than D. And there is a number of them. So it's not that you can get dimension-free estimates in this way. You can get some better estimates than what some naive approach would give, but still not dimension-free. Okay. And also here, I mean, in the case of the ball, we needed to use the Stein's result for balls here. And in the case of the cube, we needed to use a result of Jean for the continuous cube. So you need to know that the continuous counterpart is true to really make the transfer. Okay. Yeah. So before going into a further comparison of these two sets, I would like to just give an overview of the difference once again for the difference between the cube and the ball. Okay, so without going into why this is important, I'm just telling you that it's important to estimate Fourier transforms of this set. And now, well, we are not on RD, so it's not really a Fourier transform, but rather a Fourier series, say, or something like this. Okay, so the important objects for us to prove some results for the cube or for the ball are the counterparts of the Fourier transforms. For those who know the theory of Fourier transforms of abelian groups, there are really Fourier transforms on the group ZD, basically, instead of RD. Okay, so the first object is the Fourier transform for the cube Q. It's empty Q of psi, and it's just the average over the exponentials. So as it was in the continuous case, it was, well, there was no average there because remember in the continuous case, we could assume that G, the back measure is 1. So it was not appearing in front because it was 1. It was just the integral over the set. But now we cannot change the G. We have to stick with T again. So we make just an average of this sort with these exponentials. Okay, so it's an exponential sum basically, not an exponential integral, but an exponential sum. And exponential sums are often connected with number theory, and we'll see in a moment that this is also true for some parts of the arguments that we need. Okay, and another point is what is the Fourier transform for the ball, where it's pretty much the same thing, only that here we have TB intersected with ZD, and here we are summing over TB intersected with ZD. So only difference is that we are summing over different sets. So for example, because we have these averages, it's easy to see that both m's, when you compute them at 0, they are 1. Yeah, because if I just take 0, then it means that there are no exponentials here. E to the power 0 is 1. So if I have taken 0, then all the exponentials are 1. So we are summing ones and then dividing by the number of ones that we were summing. So it's 1 in this case. Okay, here psi, since we are not on RD anymore, psi has to be restricted to this set. It's called the torus, and the specific version of the torus I would like to use is just thinking that this minus 1/2 to the power d. Okay, because these functions are periodic there, so it doesn't matter it's enough to consider them only on this set, not on others. Okay, so yeah, they look like this. One looks like that, the other like that. Okay, so yeah, the objects that are important to us are these two, and I would like to tell you something about NTQ, why perhaps it's easier, well, not perhaps, why it's easier to estimate than MTB, which is much harder. Okay, so first going to the cube case. So now for the time being, I will be just speaking about the cube, G equal cube. Okay. So first thing to observe is that if the integer parts of T, two numbers, T and S, are the same, then these sets are the same. Why is it true? Well, because in the definition, this set can be thought of exactly as the set of those x's in ZD, such that the maximum coordinate xi is smaller than s. But x's are from ZD, which means that each of the coordinate is an integer. So for an integer, it only matters if these quantities here are integer to really distinguish anything. So for example, if we had here 3, it would be the same as we had here 3 and 1/2, because the integer is smaller than 3, even only if it's smaller than 3/2. So for the integers, it only matters if the t's or s's are integers. And for this reason, we may, without loss of generality, take just both in the averaging operators and in the maximal functions t which are integers. In the definition in the beginning, there was a supremum over all t is greater than 0. But for this particular question, only t's that are integers matter, natural numbers even. Okay, and another point, which is so this happens also for other sets, but the second point that is crucial, and it is very much connected with the cube, is that we can give the number, write a formula for the number of lattice points in this set. So TQ intersected with ZD turns out to be exactly this. Whereas for the ball, you don't have a number. You have the number which is called the number of lattice points in the ball, but this number is hard to do anything reasonable with it, especially when the radius is small. For the cube, it is very explicit, and it is this quantity. And the reason is that the cube has a product structure. So the cube in RD is just the product of segments, -1, 1, d times, producted d times. Okay. For similar reasons, you can explicitly rewrite the formula for the Fourier transform from the sum to this expression. It's an exercise in summing geometric series, basically. But you can do it, and you have a very explicit formula. Very explicit, more explicit than the one before for the Fourier transform of the cube. So you see that you have 1/2t plus 1 to the d. Then you have I see I written it wrongly. Sorry. If I have written this one here, then it shouldn't be. So yeah, the formula is that you have 1 over t, 2t plus 1 to the d, and then this quantity. From this formula, one can see that this is, for example, bounded by 1, which was also obvious from other formulas, but it is useful also for other purposes, as I will try to show you in a moment. Okay, so we have these very explicit formulas exactly because the cube has a product structure, and the ball does not have a product structure. So it will also already says that there will be some problems with the ball later if you want to say something for the ball. Okay, and what we would like to prove? I'm trying to give a flavor that Fourier transform estimates are important for these kinds of questions. And we had some Fourier transform estimates in the continuous setting. I said that they cannot be transferred to the discrete setting, and this is true. But it turns out that for the cube, you can prove essentially the same Fourier transform estimates, not using the continuous setting, but just working by hand with these expressions that you have. Okay, so what happens for the cube is that you have all the free estimates that you had in the continuous setting appropriately scaled. Because I remember that I couldn't say that just now t is equal to 1, because we don't have this kind of scaling anymore, but I could just leave t by and say what the estimate would be. So mtq minus 1, the estimate at 0, says that you have xi times t. mtq of xi at infinity says that you have t times xi inverse. And then this is a replacement for the estimate, the differential estimate. So the difference of mt at one time versus m at other time gets a decay in t1 and t2 and times the difference of those two. So this is what is a replacement for the differential estimate. And one may ask immediately, I mean, I said that they are similar to what happened in the continuous setting. So where is the L of g? Yeah, there was an L of g in the continuous estimates. Here it is not present for the reason that for the cube, L of g is equal 1 over 12. So it's a constant which gets eaten in those constants here. By the way, here should be a constant as well. Yeah, so it's a constant that gets eaten in those estimates. So for the cube, later on I will write it explicitly that this isotropic constant is constant, is 1 over 12. It doesn't change in the dimension, so it's not seen here. But anyway, these are exactly the estimates that these are the estimates that are closest, in a closest possible way, similar to those that we had in the continuous setting. So if we had these free estimates, and we do have them because we proved it 3 years ago, then you can, well, fine-tune the argument in the continuous setting to get something for the maximal function over the discrete cube. It's not obvious how to do it, but this lies at the heart of the proof if you go into the details. So there is some machinery which had to be built from scratch in the discrete setting, but it was built, and then it turned out that this reduces to this Fourier transform estimates. So I'm saying it's Fourier transform estimate, but all of these things are finite exponential sums. So if somebody does not like the word Fourier transform, he may say that you just need to estimate the sum of sines and cosines, because e to the 2 pi I x psi can be written as cosines and sines. So it's just an estimate for a finite sum of exponentials or of cosines of sines. You can give it as a problem to somebody who knows what is a sine and a cosine, but it's not so easy to do, as it turns out. I mean, in the cube, it's not so hard either, but later we'll see that it's a bit more difficult. Okay, so having these estimates, okay, sorry. Before saying what is the use of these estimates, I would like to mention why they are possible in the discrete setting. So it's not that they are obvious. Some of them are easy, for example, the first one, but the last two and 3 are not so obvious. But it turns out that they can be sometimes reduced to the continuous estimate. And for example, this is the case for the estimate number 3. Okay, so 3 is this one. And the way one can prove it is by referring to the appropriate estimate in the continuous setting. So you take the symmetric convex body G to be Q1/2 this time. Okay, and then you make this mu T of psi to be this average over these scalings. One can see that this has this property. I mean, it's not extremely important what are the exact formulas, but I'm just saying that this is a continuous object, which we would like to compare. So there is a canonical continuous object to which it is convenient to compare what we are having. Okay, so it's called mu T, this continuous object. Okay, and as I mentioned, it's nice that L of Q1/2 is 1 over 12, because this means that for this continuous object, we can use Bourgain's estimate forgetting about L. There was an L, but it is 1 over 12, so it can be eaten in the constants, and we don't need to care about it anymore. So this is the translation of Bourgain's estimates, the continuous ones for the object called mu t. Minus 1 is 1 over 50, 1 over 50, I forgot about the L. Yeah. And then by the mean value theorem, so this is the estimate at 0, at infinity, and then there was a differential estimate, and we would like a difference estimate because we are in the continuous set. So using a short argument, which I don't have time to go over, you can say that this is controlled by this, just mean value theorem and the differential estimate. Because for mu t, you initially have a differential estimate. Okay, so we have the estimate for mu t minus mu t1 minus mu t2. Okay, what's the reason for that? Well, we are interested not in this object, but in M2Q, in MTQ. But one can be rated to the other in a way that gives what we want, as you will see in a moment. Okay. Okay, so the idea to get, for example, the estimate for MT1 minus MT2 is to compare it with MT1 minus MT2. So we make this obvious splitting, MT1 minus MT2. It's MT1 is here, MT2 is here, and then we wrote some extra terms so that they can cancel, but it's convenient to arrange them in a different order. So for example, MT1 is here, T1 is here, cancels, perfect. T2 is here, T2 is here, everything cancels. So we could have written it in this way if we wanted. But now we group the terms in this way. Okay, so the first term is the Fourier transform for the cube, the discrete one, minus the continuous one. The second is the same, and the third is just the difference of the two continuous ones. So the difference of the continuous ones, we already said that it has convenient estimates. I mean, these estimates before by referring to the differential estimate of Bourgain. So what remains is to compare the discrete one with the continuous one. But once again, not only MTQ has explicit formula, I mean more explicit than just being a sum, but also nu t, because it is the Fourier transform of the cube. So it is also a product object of a product type. So nu t has this estimate, sorry, has this expression. Again, I see that I put wrongly here this. Okay, so it's this expression, and the difference between this one and the one for the discrete cube was that in the discrete setting, we didn't have this thing here, but rather something like this. 2 times t plus 1 times sine of pi ck, which means that the discrete thing was larger because sine of pi ck is smaller than ck, it's smaller than pi ck. So if we reverse the denominator with the numerator, you get a larger thing. So in a way, the discrete thing is larger, but not so much larger. Gauss really travels. Okay, so if you write explicitly the formulas for the difference, it's this. Then you make some computation. It turns out that it is the initial thing, MTQ of psi, the discrete one, times factor 1 minus mu 0 of psi. Okay, so we wrote the formula, an explicit formula for MTQ minus mu 2. Okay, why is this formula useful? Well, because we know all the estimates for both MTQ and 1 minus mu 0 of psi. If you put up those estimates together, you get that. So this comes from 1 minus mu 0 of psi, and this comes from MTQ of psi. Let me show you a bit about what's there. Okay, so you see, one estimate. We used one estimate for this expression and the other for this, and we just put them together. So you get c times psi times 1 over t times psi, because taking as a black box the estimate for MTQ at infinity. I didn't want to go over this, but this can be proved by direct computation. Not obvious, but direct, I mean, without reference to anything else. Okay, so you get c over psi and then 1 over t over psi, and then what happens is that psi cancels. And what remains is c over t. And with that, we are already happy because we didn't really want it for t, but for t1 and t2. But now if t1 is equal to t2, then this is 0, because we have exactly the same objects. So the interesting t1s and t2s are not the same t1s and t2s. So this means, for example, that for free, for the interesting t1s and t2s, we can write it in front. Because there are, I said that we can restrict to integer points. And if the integer points the difference of the integer points, if it's smaller than 1, then it's 0, and this is even only if. So if it's not 0, then the difference has to be larger than 1. So I can write for free t1 minus t2 in front of here, which means if I go back to the expression that I had, that mt1 minus mt2 is this thing, and this came from the last part, this comes from this part, and this comes from this part. Without the t1 and t2, we have it here, but we didn't have t1 minus t2 because I said the only ones that matter are different, so we can put it for free in those estimates here. We can add it for free here and here. Okay, and then I need to take the maximum because I don't know which one is larger. Is t1 inverse larger or t2 inverse larger? Okay, so we can prove these estimates because we very much relied on the fact that the comparison with the continuous object, continuous Fourier transform, is very exact. So once we have proved this estimate with some standard, well, not extremely standard, but known techniques, we can proceed to give the same result for the cubes as the most general known in the continuous setting. So it turns out that if you take p between 3/2 and infinity, then the discrete maximal function over the cubes has dimension 3 estimates. And it really is implied just by discrete Fourier transform estimates. So they are really at the heart of the matter here. So we are not able to cover p between 1/3/2, and it seems to require new ideas because Bourgain's proof for the cube also came much later than the general one, namely because there were some new ideas needed. So we couldn't push those ideas from the continuous setting to the discrete setup. Okay, so this is the cube. For the cube, we could prove something, but let me now go to the ball and say what are the problems for the ball in the last part of my talk. Okay, so now G is equal to B to the ball. And now if we think about the quantity sum of xi squareds, when is it smaller than t squared? Then it is the same as we didn't take t squared, but the integer part. Once again, because these coordinates here are integers. So if you add an integer, it makes always a leap at least of one step. So it doesn't matter if you have t here or on the integer part of t, which means that the interesting t's are such that t squared is a natural number in the questions, and it means that t belongs to this set square root of n. So square root of natural numbers are the only interesting points for the question on the ball, for the number of lattice points in the ball, for example. Okay, so it's easy, not easy, but it's not really hard to see that this number of lattice points in the ball is comparable to the Lebesgue measure of the ball when the radius t is this. So not incidentally, it coincides with the radius which we knew for our comparison principle, that in this radius we can prove maximal estimates, deducing the discrete ones from the continuous ones. So this is actually this is an easy exercise with just thinking that the number of lattice points can be related to putting cubes with centers at those lattice points, and then if you think how they can be arranged, then you can get this estimate. This is essentially the Lebesgue measure of the set. Okay, but by the comparison principle, we are really interested anyway in t smaller than that, so it's not really going to help that we have this estimate there. Okay, the problem is that for t very small, smaller than this, and especially very small, the number of lattice points starts to behave in a completely different way than in the continuous setting. For example, if you take t smaller than 1, then the number of lattice points inside the ball of radius t is 1, because the only lattice point for which the length is smaller than 1 is 0. But the Lebesgue measure of this set is TB. Okay, so let's say t is equal to 1/2, or maybe t to the d, and then the Lebesgue measure of b. But the problem is that the Lebesgue measure of b goes to 0 very fast with the dimension. It's well known and computed explicitly the value of this thing. So the behavior is completely different, because for in the discrete setting, the number of lattice points stays 1 all the time, whereas in the continuous setting, it gets smaller and smaller. So it's not at all that you can compare those two words for small values of t. Okay. This is, by the way, this is just a remark that the question on I said before that this number of lattice points is known to be essentially the Lebesgue measure of b times td, but the question on the remainder for d equal to 2 is a major open question in analytic number theory called Gauss circle problem. So the question, what is the best estimate for the remainder, in d equal to 2, so say d equals 2, and we are asking about this expression and what is the size of the remainder. So Gauss knew that the size of the remainder is at most this, and everybody can prove it by himself, more or less. But the conjecture is that it is this. Epsilon is an arbitrarily small exponent, so almost square root of t. So there are some partial results, for example, one by Sierpiński at the beginning of at the turn of the 19th and 20th century, that you can take not exactly t to the 1/2 plus epsilon, but e to the 2/3. So his argument used Fourier analysis, and it was quite surprising to people at this point that you can already lower the exponent. The conjecture is that you can get 1/2. I think this is a question of the level of the fields method, more or less, I suppose. I mean, open for many years and quite perceived to be quite hard in analytic number theory. Okay, but coming back to our problem, yeah, I said that there is a problem in counting lattice points in the ball, but we are not really just needing to do that, but to say something about the exponential sum, for which a prerequisite probably is to understand this, but there is a sum over there of some functions, some trigonometric functions, which we need to estimate later. So it's a more difficult question in a way than just speaking about the size of the set TB intersected with ZD. However, something is possible and something is quite easy to see. For example, it's easy to get the estimate at 0 in this way. Okay, I'm not going to show you how, but after a moment's thought, one can do it. And the point is that you don't have, like for the cube, we had t times modulus of psi, remember? So for the cube, it was this, for cube. Okay, now we have q over the square root of d, and the reason basically is that the cube almost was in the isotropic position, and the ball is not in the isotropic position. You have to scale it by square root of d, which on the Fourier transform side goes into the denominator. So it's related with the fact that, well, the ball is not in the isotropic position. You have to square it more than the cube to get it in the isotropic position. So you have this estimate. You can prove it by hand, and so this is the estimate at 0, which we have. But we would like to really make the machinery work, because we are trying to get the machinery that we run for the cube and in the continuous setting to work here. So we need to have some estimates for the Fourier transforms. So we are not very unhappy that there is the square root over d here, because essentially it's like we will be thinking about it as this constant L. And I said it does not matter if L is there or not, as long as we have it here in the, as long as it is glued in the same way to both modulus of psi and psi to the power, to inverse power. Okay, so we have it here. It's not such a problem for the time being. Okay. Yeah, for the discrete cube, you had this. This is the comment I had on the ball. But now the lemma suggests that we define this constant. So k is a constant that depends on, it's not a constant, it's a quantity that depends on t and the dimension. It's t squared by t divided by square root of d. And we would like to give estimate in terms of this constant. Okay, so in place of this estimate for the cube, with the constant 1, no square root of d here, we would like, for example, this estimate, c over kappa times psi, because it will arrange very well with the previous estimate at 0 that we had before. But the problem is that we can't prove it. We can prove something weaker, which gives some weaker result, but not this one. And we don't know if it is true. Maybe it's not true in the small scale, because some hints suggest that it's not true, but still we don't know how to prove this one. But we are able to prove something weaker, which is enough to some purposes. So there are two imported regimes. Once again, there is a distinction for two imported regimes of kappa. So recall that kappa was this, t over the square root of d. Okay, so the first regime is where kappa is greater than 1, which just translates that t is greater than square root of d. And in this regime, we are able to prove this estimate. So with this, we are very happy about, but the problem is that there is another nasty kappa to minus 1/7 here. Okay, it's not as bad as it would be if kappa is smaller than 1, because at least it may be large. Since kappa, we said that it is greater than 1, maybe this is a large quantity, so maybe it's not so bad that we have it here. Whereas for t smaller than the square root of d, which means kappa is smaller than 1, we have one term which is even better than this, because this was kappa times psi here, and here we have, sorry, this is wrong, should be kappa squared. Also here. Okay, so we have kappa times psi, the negative exponential of it, which is much better than this, Yeah, with that we are very happy, but unfortunately there's another exponential with a shifted sign. So we have an estimate of a different sort, which maybe can give something, but not all that we would like to have. But anyway, so you see that we have some replacement for the estimate. We have a very good estimate at 0. We have some estimates at infinity, maybe not so good, but maybe they are enough. But the problem is that we have no idea how to prove the estimate for the difference, because comparing with the ball does not seem to work so much as it was in the cube. So the major question would be if we can estimate this, but we cannot so far. I mean, we can for large values of t, which we don't care about, because anyway the result is known by a comparison with the continuous setting. Okay, so this seems quite hard, mainly because, as I said, the sort of the methods of number theory that work for large values of t, they do not seem to work for small values of t because the objects are different. So we could prove this result above for the estimates at infinity by using some combinatories, at least for some small scales, and we don't know how to proceed with for this estimate for the difference. What we could prove with using the results for the Fourier transform estimate, so only using the result at 0 and at infinity, only those two we have, we don't know the result for the difference. So using the results at 0 at infinity, we could prove that you have a dimension 3 estimate on L2, but only if you take time being something which is called a dyadic number. So if you restrict the supremum to powers of 2. So 2, 4, 8, 16, etc., but not for all values of t. So this is already not obvious because the number, for example, of the quantities 2 to the n, the number of n's that are between 1 and the number of n's that satisfy 2 to the n less than b, say this, is about the log of d. So it grows with the dimension. So it is not obvious that this result is true. And actually, to prove it, you have to really make quite an effort to do it. But still, we do not know how to prove the general case of the full maximal function. Okay, I had a sketch of the proof, but I think I'm running out of time, so this is probably a good point to stop.
Can you hear? No. Okay, now? Okay, so maybe we may pass to the questions. Are there any questions? Or, and maybe some questions online? No?
I have a question.
Please.
Somebody.
Someone online maybe.
Yeah, but I can hear.
Okay. Is there anyone asking question online? No. Okay.
So my question is the following: what is the reason for the appearance of the exponent 3/2, where these estimates are significant?
Okay, so the reason is that you prove this by, well, at the very bottom line, there is an interpolation point. So basically, there is a very good estimate on L2 for some object, which gives, say, 2 to the minus j on L2. And there is another estimate. Yeah, maybe I can even try to write it down somewhere. Okay, so there is one estimate that is very good on L2. Just a second. So at the very bottom of the argument, you have a number of operators. You have a series of operators, say Tj. Okay, and you know that Tj on L2 decays as something like 2 to the minus j. I don't remember. So then there are indexed by integers. And on the other hand, you know that for these operators, you have some estimate on L1, which grows with j, like t to the, I don't remember exactly what to put in the exponent to really get 3/2, but say 2 to the j. And now you would like to interpolate, because the operator that you are interested in is not just single tj, but the full sum. Okay. So if you interpolate, you will get that t is smaller than the sum over tj's in any norms, and say LP norm. Okay, but now interpolation will tell you that if you are close to L2, you will get negative exponent, whereas you are close to L1, you will get a positive exponent. So positive geometric series cannot be summed, whereas negative geometric series is summable. So if you play with the exponents, you will realize that the point where this breaks is 3/2. And yeah, you're welcome.
Okay, are there any other questions? Well, if not, maybe we may applaud the speaker. And I suggest we reconvene at 11:10. Okay, a break until 11:10. Mm-hmm.